So this formula for the ideal gas law is PV-NRT. PV equals nRT. You hopefully see some familiar variables and then perhaps some not so familiar variables as well. That's okay. P, I think we're pretty used to that one. That stands for pressure. V, we're also probably pretty familiar with that one. Stands for volume. Kind of a quick little twist here. So far, all the other gas laws we worked with, so Charles's law, Gay-Lussac's law, Boyle's law, the combined law, the volume didn't matter. Like you could use milliliters, you use liters, you use gallons if you wanted to. It didn't matter. Now it does. When you use PV-NRT, your volume must be in liters. So kind of watch out for that. The other ones, it didn't matter, but for PV-NRT, it does. All right, N, there's a new variable. We haven't looked at N yet. And this is what makes this law so useful. N stands for moles. So now with PV-NRT, we can figure out how much of the gas is there, which allows us to do all sorts of things, like find out how many particles or what mass of gas or how much energy, do all sorts of things because we can get to moles. R is also new variable there. R is the ideal gas constant. We'll talk about in just a second here. The word constant is kind of misleading, not really, but kind of misleading. And then finally we have T, and that one is familiar to us. That is temperature. And that must be in Kelvin. Like all of our other gas laws. So nothing new about that. Get used to adding that 273. Must work in Kelvin. All right, so there's the variables for PV-NRT, the ideal gas law. Here are the R values. So like I said, normally when we think of a constant, we think of a number that doesn't change. That's kind of true, except for the fact that we have multiple R values. There's actually several other R values as well, but these are the two we're going to use most frequently. So these are the two we need to know. And again, kind of confusing. Usually when we think of a constant, we think just one number. It never changes. Here we have different constants. Why? What's the difference? Anybody notice what the difference is between those two? Excellent. Yep, perfect. Guys, here's the difference. One of them is when your pressure is in atmospheres, and the other is when your pressure is in kilopascals. So you have to be careful. You have to pay attention. You have to make sure you are aware of what your pressure is being measured in. So if your pressure is being measured in atmospheres, you want to use this R value. If your pressure is being measured in kilopascals, you want to make sure you use this R value. So watch your units, super, super important. Like all of this chapter, units are everything. Cool. Questions so far? All right, let's see this bad boy in action then, huh? I messed up. The milliliters right here, milliliters. All right, so our first example here says, when the temperature of a rigid hollow sphere containing 685 milliliters of helium gas is held to 621 Kelvin, the pressure of the gas is 1.89 times 10 to the third kilopascals. How many moles of helium does the sphere hold? Well, a couple different ways to know we're working with PivNert. First and foremost, they're asking for moles. The only formula we have so far that works with moles is PivNert. That in value. All the other ones just solve for pressure and volume and temperature. But this one has moles, so if we ever have moles in the question, we know we're using PivNert. Secondly, you've only got one of all the different variables, like only one temperature, only one volume, only one pressure. Remember, for all those other ones, the temperature or the volume or the pressure changes. You have a P1 and a P2, a V1 and a V2. So only one of every variable, and it's asking for moles, definitely working with PivNert. All right, so our pressure, let's look for that. Our pressure, 1.89 times 10 to the third kPa. We should recognize kPa plus the words themselves, the pressure of the gases. So there we go, definitely the pressure. The volume, 685 milliliters. Now, don't forget, we can't work with milliliters. We need to convert it to liters. Thousand milliliters in a liter. 685 divided by 1,000, 0.685. Our N value, and that's our number of moles. That's what we're looking for. Our R value, we have to choose the right one. So what's our unit of pressure? Kilopascals. So we go up, we have to use the 8.314 because that's the one that works with kilopascals. And finally, our temperature, 621 Kelvin. Hey, it's nice when they give it to us in Kelvin. We don't have to do any conversions or anything. We just already got it in Kelvin. All right, so there are our variables. Now we're ready to start thinking about the formula. PivNert. Again, guys, my biggest recommendation, isolate your variable first. We are looking for N. Let's get that on the side by itself right now. Let's not start throwing numbers at it. That just gets way too confusing. So I have P times V is equal to N times R times T. The opposite of times R times T is divided by R times T. So if I divide both sides by R times T, I'll get them off the right. Now I've got my N on the side by itself, and that means I'm ready to plug in my variables and eventually solve. So my pressure, 1.89 times 10 to the third kilopascals times 0.685 liters divided by my R value is 8.314 liters times kPa over K times moles. Yes, you do need to show your work. Show your units. I need to see that. I know it's a big, nasty one, but I need to see that. That's how all the units cancel out, is only because it's there. If it's not there, all the units don't cancel out. And 621 Kelvin. All of that together will give me my N value. Now we're ready to crunch our numbers, calculate 1.89. I'm going to use the second big E. Again, that big E there stands for times 10 to the power of. So I just hit 3 now. So 1.89 big E 3 times 0.685 divided by 8.314 divided by, I know it says times, but that number is on the bottom. We have to divide by it. You insist on hitting the times button, fine. Make sure you put this in the parentheses on the bottom. But I'm just going to hit the divided by button, 621. Press the enter button, and voila. There's my number of moles. 3 significant digits, 3 significant digits, 4 significant digits, and 3 significant digits. We're limited to just 3. So that's the 2, the 5, and the 0. The number after the 0 is definitely enough to round up. So we'll say 0.251 moles of helium. There we go. Not too bad, huh? All right, I want to give you one more example so you don't freak out when you see this type of question. It's not that bad. Not that bad. All right, so second example here. What mass of oxygen gas is in a 30 liter, so there's a volume, scuba canister if the temperature is 27 degrees Celsius and the pressure is 200 atmospheres? Here's why people freak out when they see this one. We don't know how to solve for mass. People always get confused, like, well, there's no variable for mass. N is for moles, but there's nothing for mass. And you'd be right, there isn't. But here's the thing, guys, you can all very easily go from moles to mass. We've been doing that since like chapter 2 this year. Moles to mass is really, really easy. We're all very capable of it. So if we can use all this, solve for our moles, once we have our moles, get into the mass is a piece of cake. Something we've been doing for months now. So let's list out our variables here. Our pressure, the last thing they gave us, 200 decimal point ATM. Yeah, the decimal point is important. It means all these are significant. The volume is 30 liters. The number of moles, again, I know that's not what the question's asking for, but we have to sit here and we have to say, hey, we can go moles to grams. So let's solve for moles. That's our question mark. Our R value, well, let's choose the right one. We're working with atmospheres this time. We'll work with the 0.0821 value. And our temperature, they tell us, is 27 degrees Celsius. Hey guys, make sure you are converting to Kelvin. It cost a few of you guys some points on homework last week. You have to always convert to Kelvin. Add 273, 300 Kelvin. Again, that decimal point is important. This is an addition problem. It doesn't matter how many sig figs we have. It matters what placeholder the last one is in. This is in the ones column. This is in the ones column. So our last digit needs to be in the ones column. The only way to do that is to put a decimal after it. Now that 0 is significant. Cool. All right, so we are ready to set this guy up now. And let's isolate for the variable we're looking for. In. We just did it, so it shouldn't be too hard. We need to divide out R times T. There we go. Now we're ready to plug in our variables. P, 200 ATM. V, 30.0 liters. R, 0.0821 liters times atmospheres divided by Kelvin times moles. And our temperature, 300 Kelvin. All that will give us our number of moles in. Again, make sure you're dividing by 300 here. I know it looks like it's times 300, but that's only because it's on the bottom. On the bottom, divide it. There we go. Then normally I'd say, okay, 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. I'd call it 3 sig figs, but here's the thing. This is not our final answer. Remember, we still need to take this value of moles and convert it into grams, the mass. This is not my final answer, which means I want to carry at least 2 extra digits. So I'm going to say the 2. Write my variable first. N equals the 2, the 4, the 3. There's my 3 significant digits, and then I'm going to carry at least 2 extras. The 6 and the 0. That 5 is enough to have us round up. So it's a 243.61 moles of oxygen. Don't forget, oxygen is a diatomic. Never by itself. Has to be O2. That'll come really important here in the next step. So I'm going to underline That 6-1, they're not significant. I want to remind myself, hey, I've only got 6 sig figs. I just don't want to round off yet. Might affect me. Might get round off here. Cool. All right, final step. Now we got to do what we have been doing for 10 chapters now. We need to go moles to mass. How much mass of O2 is in 243.61 moles of O2? So what mass of O2 is in 243.61 moles of O2? Well, 1 mole of O2 will have a mass of what? Well, this is where we use our periodic table. There's oxygen. Remember, it's O2, so we have to say 15.9994 times 2. There's our mass of O2 per mole. .9988 grams of O2 per 1 mole of O2. And now we're ready to do our multiplication then. 243.61 times 31.9988. Press the enter button. 7795.227668. Now we can round to our significant digits. Because now this is a final answer. So again, I want 3 significant digits here. That'd be the 7, the 7, and the 9. 5 is enough to round that 9 up. So that means we're going to have 7,800 grams of O2. Kind of a problem with this. I need 3 significant digits. How can I get 3 significant digits? Right now I've got 2. If I put a decimal at the end of this, now I've got 4. So that makes both of those zeros significant. How can I get just 3 significant digits? Say one more time. We could. So this would definitely be 3 significant digits, but unfortunately that's a little bit too much rounding. I want exactly 7,800. And although you're right, this is 3 significant digits, 10 more than what I think I have. So I can't do it that way. Mike? Yes. Yep, this is one we're going to have to write it in scientific notation. So you're always welcome to write it in scientific notation, and sometimes you have to. This is one where we're going to have to write this in scientific notation. It's the only way to get the appropriate digits and keep the number that we want. So 7.80. Now we've got our 3 significant digits. The times 10 to the third makes it 1,000. So 7,800, like we thought. There we go. That's our mass of oxygen. That might seem like a lot, but it's not. It's not really that much. It's like 35 pounds. It's not too bad. You know, it's not light, but it certainly isn't heavy. 35 pounds of oxygen. Questions?